Not putting into I missed. I realized that I had not accounted for the case. For my values are the same. Since I have this infinite state possibility, right? And I'm infinitely looping this infinite heuristic of values.
That'll break your algorithm.
So after 4 hours, I saw the equal sign there went from 0 success to I had to change my sentence 6 times. Trying to figure out what's going on, but this is that doesn't value.
You know, me taking my heuristic was just because I came up with a bunch of really dumb heuristics. Like at one point after 4 separate heuristics, I did not know of the function at the bottom, the get basis, and so it's like taking the max of 4 different heuristics. I was like, why the hell does this not work? Getting 9,500 nodes.
Yeah.
Not doing anything.
I have to figure out my
Are you done with the project?
yes.
Are you handed it in? Because I still have
Because my grade scope isn't like my code, so I'm going there, make sure I don't have any beautiful design on the blocks and stuff like that. But I know for a fact that I definitely tried to implement the multi-iconic block at least 3 separate occasions. And I don't know if I can do that.
if you put any so 5. I'm gonna go sit
I have a terrible decision.
Markov.
I guess it's not.
I'm tempted to write the date anyway, which I'm going to do. What date is it?
Get my gamer tag.
Oh yeah. Well, nothing wrong with talking more about no meeting at all. I don't know what you're supposed to do with this kind
Let's go back to that.
Yeah, that would have been better.
Yeah, but what I had.
Fine.
So I need to go backwards in time.
We weren't trying to do better.
Yeah, so you should start looking at this and figure out what the answers are. True false statements.
I have a question for you. Now, this line will look good. Right down this column. Versus that.
It's
Yours isn't. Yours isn't both. Mine is not. So, and it's nothing wrong with that.
Am I alive?
I think.
Yeah. Never played the smart person.
You go by John,
I barely sleep.
You have to think between five.
It probably would make my life better though. It's fun. So, yeah. It's a point class. I haven't done anything in it, but it's a point class. Essentially. Yeah. I didn't realize
Okay, so we will get started. So you are supposed to have watched the MVP setup lecture. So this is sort of a sanity test of, I mean, you're not being graded, but I want to make sure that we're on the same page. So I'll ask each of them, and maybe you guys can say, I might, and then I might ask one of you probably explain for that. We'll see. So the first statement, each of these are like either true or false, and the question is it true or false, and why? Right? So if you understood the lecture, then if you saw the lecture, at least it should sort of vaguely remind you of something. And if you understood it, then you can also understand the differences. So you guys did see that MDPs are basically, you specify them using this transition function and reward function and all that stuff. So you saw the entire lecture. I'm being told by a couple of you at least that I'm repeating too much of the thing that I made you watch. So I will try not to today. And then, so those of you who took a chance and not watch would have picked the worst day, because it turns out MDPs, if you haven't heard it, the second time it's still hard to completely wrap your head around it. The first time, without me telling you all over again, it'll be quite hard. Okay. So anyway, so the first question is, the reward of a state in an MDP is proportional to its value, true or false? This should be like true means it's always must be true. The reward of a state in an MDP is proportional to its value. Yes.
Will you go over what is the difference between a reward and a value?
Okay, I'll get there. Anybody else? Anybody else? Okay. So the the best way to actually for you to remember the difference is actually, even though people never teach MDPs and A star as if they are connected, as I said, everything is connected to everything. And the best way you learn is by connecting the new stuff, the stuff that you already know. Okay. So if you know A star, we talked in terms of costs, the edge cost and the optimal cost to the goal. In the standard MDP, we talked about rewards, immediate rewards and long-term values. Okay. But rewards and values are just the negatives of costs and optimal costs. So in fact, in the end of the lecture that you have seen, the picture with Dimitri Bertsekas, standing in front of the wall of, the brickyard with a dynamic programming equation for cost-oriented MDPs. So you can think of maximizing the reward or minimizing the cost. You can think of your goal in life is to maximize happiness or minimize unhappiness. Either which way, it's basically equivalent. So in the case of minimizing unhappiness, you think of everything as a chore. Everything is a cost. And I just want to reduce the amount of cost. In the way of looking at a positive way, everything is a reward. I want to increase the reward. In the case of rewards, if in fact the reward is negative, that means it's actually a positive cost. In the case of cost, if the cost is negative, that means it's actually a reward. In A star search, you didn't have obviously negative costs because for A star to converge, you needed to have positive costs. So the reward and value in terms of A star search is reward is really the edge cost. Value is the value to go, or how much is the cost to go. So you think of H star. H star or the heuristic approximation or H star is a perfectly heuristic. Value, optimal value is basically equal to optimal cost to go. You see what I'm saying? So we use, again, we'll do this today too. We use these two kinds of notations, reward and value on one hand, and cost to go on the other hand. They're basically, most of the time, reinforcement learning people use R and V because they think of the world as positive rewards. And just a second, okay? And then they try to optimize the long-term cumulative reward. And in particular, a value of a state is how much cumulative reward do you think you will get if you do the best actions possible from there onwards. That's like A star searches H star. What is the least cost from this node to the goal if you were to pick the right set of actions to go to the goal? You see what I'm saying? So obviously, edge cost to come to a state has nothing whatsoever to do with how far that state is from the nearest goal. Similarly, immediate reward has nothing to do with long-term value in general, which is why a myopic agent, that means an agent which only looks at the immediate reward, winds up making mistakes. You see what I'm saying? So if you look ahead, you will be able to see that actually this reward, even though this state seems to have a positive reward, from here onwards, what you can achieve from this state is not as good as this other state, which has a negative reward. So my classic example, I don't know whether I said it in this lecture or said in the other lecture, but my classic example is imagine the state of being outside the class, enjoying the weather. It's not that good a weather today, or being inside the class, listening to me. I mean, immediate reward, who are we kidding? Immediate reward outside is better. Right? I mean, I think that I'm a good lecturer, but clearly, who am I kidding? So outside is way better immediate reward wise than being stuck here. The only reason you are sitting here is because you somehow think that the long-term value from this state, having learned AI, you can do a lot more interesting things in your life. Whereas hanging around outside, you will have fun right now, but nothing much more. And an intelligent agent essentially is one which is able to look ahead and see beyond the immediate reward. And so the only times when reward is actually proportional to the value, it's either because it's a very easy problem, that means even myopic agents will be able to do well in that problem, or you made it so that some agent of yours that you like to succeed, they can do myopic reasoning and still succeed. Do you understand what I'm saying? So my favorite example for that is, how do you get Homer Simpson to get to the library? Homer Simpson, obviously Homer Simpson is never going to go to the library. Well, you sprinkle a whole bunch of donuts all the way to the library. So he's just following the track that you've established. So you made the state's immediate reward to be more positive than it really should be, so that it's kind of proportional to the actual long-term value, to the extent we all believe that he going to the library is actually going to be better value for him. So that idea, by the way, is called reward shaping. When we try to help a somewhat inferentially challenged agent, inferentially challenged means they want to just look at one step ahead and then try to make a decision, to do the right thing, you change the reward structure. You, the other agent, change the reward structure. Have any of you wondered why most medicines are sweet? Why should medicines be sweet at all? It's because juniors have come into this world liking sweet taste. If you tell them, take this really bitter medicine, it's going to help you, basically survive the first year, they're not going to eat it. They'll just keep throwing it away. So you change the reward of the metric of the medicine, artificially, such that it is sweet, so that they'll wind up doing the action, which actually increases their long-term value. The quote, "Now no pain, no gain," is basically saying immediate reward is likely to be negative, but the long-term reward can be positive. That's what no pain, no gain means. But you can't tell it to a little kid, saying no pain, no gain, and then slap them and try to give them a bitter medicine. They're not going to take it. So you change the reward. Question you had in the last?
I think you already answered this, but when you say cost to go, that means to go from one state to another.
No, cost to go means from that state to the nearest goal.
Nearest goal.
Yeah, so it's very important to understand that J is connected to H. The analogy between A star notation and MDP notation is that J is like H. So optimal cost to go J star is like H star. And you will get a very different understanding of MDPs when you realize that most of the algorithms we look at will be things like value iteration, which is trying to compute the V star, or in the case of cost-oriented MDPs, trying to compute the J star. So what MDP is trying to do is, rather than find the path from the start node to the goal node, it's trying to find H star for every state in the world. That looks dumb, right? Compared to A star, that looks dumb, because A star is only caring about H star for some nodes that happen to be on the optimal path to the goal. That actually also brings up the question as to why is it that MDPs have this thing called policy? Whereas A star has this thing called optimal path. Why? Yeah,
Operates in the stochastic world. And
exactly. So the problem is A star too would require policy if there is, in addition to A star, there is a pesky kid making the world a little bit dynamic. And whenever the A star does some actions, then it is deterministic as far as it is concerned. It expects if I do this action A, from state A, I do the action, go from A to B, I will be in B. For sure, I'll be in B. But then this pesky kid removes me and puts it in C, puts me in C. At that point, A star can't just say, I must be in B because according to my projections, I must be in B. Instead, it realizes that, hey, no, I'm in C. So what do I do now? So it then needs to start finding an optimal path from C. If it happens enough number of times, it is actually better to compute H star once. You see what I'm saying? All sources, shortest path. That means if you have an A star with a goal, then you're trying to find from each source what is the shortest path to that goal. At which point it doesn't matter which state you are in, you will be able to find what the shortest path is. So it's a stochasticity that made MDP go for policies. Similarly, if you remove stochasticity from MDPs, you can still compute policies. You'll basically compute H star, which is the optimal value from which you will know what to do from each state. But that's an overkill. Because if you know where you're starting from, then you know pretty much the path you will go on to the goal. Yes.
So you showed us a graph for A star for the time required to compute H star and then choosing one and then finding the path.
Well, that was H. That's the estimate of H star.
Yeah, so why would that also not apply to MDP?
You'll apply it here too.
So
You will apply here too. What?
You can find something extremely accurate for you.
Yes, my point is you have to have, you really, that's a very good question. So at one level, MDP is doing a dumb thing, but it has to do that dumb thing because it needs to, in the worst case, in a connected world with stochastic actions, after the action, you might be anywhere. So wherever you are, you should know what to do in the most general case. So between a policy which tells you what to do in every state of the world and a path which only tells you what to do for the states that fall in the optimal path to the goal, that's what A star does. There can be middle grounds. You can have a partial policy which tells you for some number of states which you think are likely to occur, you will know what to do. In fact, one other thing that MDPs can do is actually act as if it is an A star search. Even though there is stochasticity, act as if the actions are somewhat deterministic. So whichever is the most likely outcome, perhaps take that as the outcome. Compute a path. Start trying to execute it. But then when you execute, you will see that you're not actually in the state you're expected to be. So then try to find a way of going from that state to the path. That's a way of computing a somewhat suboptimal policy. So if you figured out how to go from here to some faraway place like Flagstaff or something, in the middle, suddenly you find that there's a rerouting, like, there's like some vehicle on fire on 17. You have one of two options. One is compute a new path, or just get off 17 and come back onto 17 little later. Because from there onwards, the false policy has been computed before. Yes.
So you're saying that like with like MDPs, you can also find like an optimal path just like following a policy that you.
MDP is a strict generalization of A star search. It does everything that A star search does. Right? Because A star search, so that's one of the questions actually. Let's just see, where is this? Yeah, so this is what I answered. I'm not good at asking questions. I give answers for questions. MDPs look at policies rather than plans, as A-star search does, because they consider stochastic action. That's a true statement. It's a generalization of A-star. Okay? And the little generalization goes a long way, suddenly. But it's not completely a different world. You can make connections between everything you learned in A-star and everything you learned in MDP. And that will stand you in good stead. Okay? So the next, any questions on this one? Next one, finite horizon MDP has an optimal policy that is larger than one for an infinite horizon MDP. Yes.
Larger, like more complex, is that what you're trying to say?
Larger means the size. Think of it needs more space to store it. What is a policy? A policy is a state to action mapping.
Okay, then,
Right? So, for example, if you have an MDP of k states, the policy would be of size k, because for each state you need to know what the action is. That's the general idea. But if it is that the same when the MDP is finite horizon versus infinite horizon? Again, all of this you should have heard. I mean, first of all, how many of you actually saw the lecture? Okay, the rest of you are basically lost and you picked the wrong day to take a chance, unfortunately. Okay, because if you don't see the lecture, then a lot of stuff you are trying to catch up in the middle. But so coming back to the finite horizon versus infinite horizon, I mean, I have to do it for the people who watched. That's a reasonable thing, because the last several times I did it for everybody, even who didn't watch. So this will give you extra work to go back. So those of you who saw the difference between finite and infinite, which one has bigger policy? Right? That's like a cute thing. It's a mind-blowing thing. Because we live only a certain amount of time, our optimal policy is larger than a being who lives for infinite amount of time. But it makes sense. You see what I'm saying? When you are a kid, so I mean, everything, like for example, there are obvious things like stocks, right? I mean, there was some guy who knew all about stocks, right? So they say that when you are young, you should put all your money in speculative stocks because you might hit big. But when you get to old age, unless you think that Uncle Sam can just save you with pension, you should put your money in somewhat less volatile assets like bonds. So in fact, the stock versus bond ratio is when you are young, your financial advisor will tell you the policy for you should be more stocks, less bonds. And then when you're old, more bonds, less stocks. That was old stuff. Now we have crypto and we have Tesla. So all of this is out the window. But the real stocks, that's the idea. You know, stocks are highly volatile, and so they can give you very high reward, but they can also give you very big negative, reward. And when you are young, you have time to, basically recoup from this. So you wind up having this different policy because you live only for 100 or maximum 100 or so years, depending on whether you take a vaccine or not, right? Right. So the question then is basically finite horizon actually is not just, the policy is not just the number of states, is not the size of number of states, it is number of states times the horizon. Because if I have k steps to live, k years to live, I'm in state S, what should my next action be? If I have k minus 1 steps to live, and I'm in state S, what's my next action? It makes a lot of sense. In fact, one of the things I will do in this class is that the textbook basically goes for infinite horizon MDP directly. But I will actually teach you finite horizon MDP first and say infinite horizon MDP is just a generalization. It's actually a special case in almost where the horizon k is infinite. which means that finite, in fact, if those of you who also looked at the optional example for doing finite horizon value iteration, that's only optional. So I'll look at it here again today. But those of you who looked at it, you realize it's very simple calculation to compute the policy for each of the states given k steps to go. And k minus 1 steps to go, k minus 2 steps to go. Right? And then if it is infinite horizon, then you essentially keep doing this as if these are the intermediate values until the values converge from one iteration to another iteration. And then you say, that's my value of each of the states. And once I know the values, I can always find the policy. By the way, this idea that if you know the value, you can find the policy. This is like a big thing. We sort of assume value iteration will find the value, says you can always convert into policy. That's like saying if you know H star, you can compute the optimal path very easily. And that's not surprising, because in the A star search graph, if I give you H star for each of the states, then you can in linear time figure out what the path is. You see what I'm saying? Because the richest uncle in the world is telling you, pick me, and then from here pick this, from here pick this, from here pick this, and this is the goal. So it's not surprising that you can convert value into policy, because you can convert H star into path. There was a question somewhere? Yeah.
It's just like an observation more than a question, but it could, like, would it be correct to say that in a finite horizon, it's actually possible to find an optimal policy, whereas in the infinite one, it's just not, you just don't know if there's one. So you just...
No, you will be able to find it under a variety of special cases. So one of the things we will talk about is actually, again, so the MDP is a really big generalization of a star search. So there are things that connect to a star search, but there are things also more general. So one of the interesting questions is, when the horizon becomes infinite, the biggest worry you will have is, what is, if you are in this state, what is expected reward, cumulative reward you can get? Even if each transition gives you a little positive reward, the state sequence will be infinitely large in the worst case. Infinity times a very small number is still infinity, which means it looks as if all states look the same in terms of their final valuation, which means the problem becomes degenerate. And we deal with it in two different ways, which will come to it towards the end of today's class and maybe beginning of next class. Problem becomes degenerate in the following. And so the way to stop the degeneracy is that you will say, one idea is discounting. You will say a reward later on down, k steps down, the immediate reward k steps down, n steps down, is gamma power n of the real reward. Let's say real reward is 10 for each state. Each state you get into, you get 10 units. But 10 units, 10 years, 10 steps from now is different from 10 units right now. If you want to discount future, which you do in general, like for example, if I say, I can give you $10 right now, or $10 3 years from now. No, it's $10 right now, or $100 3 years from now. Which one is better? $10 now, $100 10 years from now. Which one is better? You start, in essence, in your back of your mind, start discounting the future rewards. And the discount factor is this gamma. We'll get to that. That's how you can actually make an infinite sequence converge to a finite value. Remember geometric sequences, anybody? Gamma, as long as gamma is between 0 and strictly below 1, you will get a geometric sequence. So it's guaranteed to converge. So each different state, all of them won't have the same value to go. They will have different values, so you can actually get a unique optimal policy. A completely different way, which we won't talk about in this class at all, is to say that the point of MDPs is not to optimize the cumulative reward, but to optimize the average reward per step. An average reward per step is well defined, even if you have infinite number of steps. It turns out that those are average reward MDPs are much harder to analyze. We won't talk about it here. Okay. Okay. Reward in MDPs is like H in A star search. True or false? Yes.
Wouldn't it be the reward is more like G in it?
It's not even G, actually. It's reasonable, but it's not even G, actually. The reward is just, so one of the funny things in MDP versus A star search is A star search has a start state. And you're going from the start state to the goal state. MDPs in general, they never told you what start state is. It just said certain states will give you some kinds of rewards. The idea is to keep hanging around, living your life and collecting more and more rewards. And the policy that collects, this is your life. This is how your life is. It's not like after a goal you die. For 100 years, you're still hanging around, 100 or so years. You're trying to find the optimal policy for your life. So it's not even, there is no such thing as start state, it turns out in MDPs. Wherever you are, you need to do the right action from there. Wherever you are, you need to do the right action from there. So the actual correct connection between reward and A star search is, as I said, cost, the edge cost. That's the immediate thing that you just did. Okay, it's not even G. G is basically from some start node to here. This is just the last edge cost that you saw. Okay, any other questions on that? Okay, yeah, this one. An MDP searching generalizes A star setting by considering stochastic environments with generalized goals. True or false? True. Because you already know about the stochastic part. The generalized goal part is that there is no such thing as a single node that actually satisfies the goal criterion. You just get through goals, good states, collecting reward. Which might make you think, what stops me if they're giving candies somewhere? That's like a candy giving state. You have a donut giving state, and you've gone through this in life. What stops me from going to the same place again and again and again, getting lots and lots of candies? What? Exactly. So at some point of time, you'll start hating candies. So you'll sort of realize that utility of the 54th candy is much less than the first one. Plus, of course, we have social norms, and the people will say, hey, why don't you be here? You seem to be coming all the time. But notice that won't happen in A star search. So in fact, one of the interesting things is in A star search, once you reach the goal, then you can't go back and come back to the goal again. What is stopping you? The way to stop an agent from going to the same state again in MDP is to make that state a terminal state. That means you eat the candy, you die. Then you can't come back again. That's a little too cruel. So infinite horizon MDPs where you don't have terminal states, you better discount the reward. Otherwise, essentially, there are infinite candies. And every state has infinite candies. And that's no good. Basically, that you might think that's like a diabetes problem, but that's bigger than a diabetes problem. It is a degeneracy of the problem itself, because all states look equally good. In which case, there is no such thing as optimal policy. Okay. Okay. So one other question is, if I wrote an MDP setting, generalized A-star setting by considering stochastic environment with generalized goals and partial observability, would I be right or wrong? What?
Didn't you say there's like a POMDP for that?
I understand, but why is this not partial observable? Again, please understand what I'm trying to do is, in the ideal case, you actually heard the lecture. I know that you all have lots and lots of demands on your time. And so, but in the ideal case, you heard the lecture. The first time you would have heard the lecture, very little of it will get. So I'm sort of trying to push, in different ways, improve your intuitions. So yes, there is a POM DP later on, partially observable MDP. But the real question is, why is this not partially observable? Not you, somebody else. Like this side in general, we haven't watched and picked the wrong day not to watch. Somebody else. So why are MDPs considered fully observable? It seems to be uncertainty, right? You don't know when you do an action, you don't know which state you'll get into. It's uncertain. But why is it fully observable? Consider the act of tossing a coin. Okay, is the action static? Is the action deterministic or stochastic? Is the action deterministic or stochastic? What? Stochastic. Right? Is after the coin falls down, can you tell whether it came heads or tails? With 100% probability or not? So it is fully observable. Before doing the action, you don't know what will happen to the world. After doing the action, you know what the world is. Full observability only says you know where you are. You see what I'm saying? You just know where you are. So before you were here, you thought you would be somewhere else because of uncertainty. But then you actually fell here. But then you woke up, you check, you know exactly which state you are in. That's full observability. So in fact, MDPs, if you are into it, and if you are into what are called retronyms, do people know the word retronym, by the way? It's like a GRE thing. You are also preparing for GRE at some point of time. A retronym is a situation where you go and change the name of an old thing because some new thing happened. An example is ovens used to be called ovens. They're now called conventional ovens because there is a microwave oven. Phones used to be called phones. Now you call them landlines because there are cell phones. Similarly, MDPs, we just started calling MDPs. And then you realize there are POM DPs. So you went back and called the old MDPs POM DPs, fully observable MDPs. So normal MDPs are really fully observable MDPs. Yes.
So just to make sure that I understand, so that differs from A star because with A star you don't necessarily know like what the whole tree looks like, so it's not fully observable, or is that?
No, A star is fully observable.
Oh.
A star is deterministic and fully observable.
Oh.
But one of the strange things about A star, this is a second order issue. In the following sense, think about this. If you know the start state and your actions are deterministic, do you need eyes? Understand what I'm saying? If you are in a if you know which state you're starting from, and each of your actions are deterministic, that means they know exactly what their effect would be, which state they will take you to. Then theoretically, you don't need eyes. I mean, you may need ice because you're lazy and you didn't count exactly what actions you have done and which state you should be in by now. But really, you don't need ice anymore. So that's why A star can either be thought of as deterministic with a start state and doesn't observe at all. It's not that it's not observable, it doesn't even observe. Why does it have to observe? It knows where it is supposed to be. Or you can think of it as just fully observed. It's like a really second order point. And it sort of tells you that eyes are not always needed. Okay, sometimes eyes make up for laziness of brain. You see what I'm saying? I should know where I am, but you know what the heck? Why I have eyes, I might as well look. Or ask somebody. Those are all observations. Okay. This was done. This was done. This was done. This was done. Okay, the last one. Understanding an MDP agent learning, both its understanding an MDP agent involves learning both its transition and reward models. True or false? So how do you specify an MDP agent? How do you specify an A star agent? You specify the A star agent by providing the cost of the edges and the goal test. Then you're done. How do you specify an MDP? You specify the transition model, which says when you do an action, what states can you get? If you do this action from this state, what other states can you get with what probabilities? You see what I'm saying? So the real difference between A star and MDP is A star, if you are in S1, you do an action A1, it will say you will go to S2 with probability 1.0, because that's what deterministic means. If it is stochastic, then you say you are in S1, you do action A1, then with let's say 0.3 probability, you go to S2, 0.1 you go to S4, 0.5 you go to S7, and then 0.1 more, I guess, right? 0.1 you go to S9. That's a stochastic action. Every action that we do is actually a stochastic action. So it's like, I try to put my pen on this, mostly it's deterministic, but there's a possibility that my hand kind of misses the table and the damn thing falls down. But what happens is that our actions, if you are a good agent, if you are a costly agent with good effectors, then the probabilities would be such that some of the outcomes have much higher probability than the rest of the bad outcomes, the unexpected outcomes. That all you're doing is you are taking the probability mass of 1.0 and putting it over all the states. Suppose the world has states S1 to S10,000. When you do an action A in state S1, you need to tell me what's the probability that you will find yourself in any one of these 10,000 states. That's a uniform probability distribution. You add up all the probabilities, it should be equal to 1.0. So it turns out that for probabilities, you can actually talk of. So if you have, let's say 10,000, 1 to 10,000, and then if every state is equally likely, the probabilities will be something like that. Because each of these probabilities is 1 by 10,000. If only one state is definitely going to happen, and that is this state, here is 1.0. If you are a reasonably good robot, which actually has some states more likely that most other states are very less likely, then maybe you will be something like this. This is kind of deterministic. Not fully, but it's kind of deterministic. So all of these are distributions, probability distributions over the same number of states, 1 to 10,000. And they're differing in terms of how the probability mass is concentrated. Is it kind of split over all the states equally? Or is it unequally split. And this idea is, we'll talk about much later. This idea is called entropy of a distribution. High entropy is fully uniform distribution. Zero entropy means only one state. You guys, any of you have done thermodynamics? You heard of the word entropy? Just like ergodicity, entropy is the other thing that you should always use in party conversations to make sure that you tell them you are smarter than them and they can realize that you're a viewer than them. Okay? Entropy. Entropy is a measure of the disorder in the universe. So from the perspective of the probability, the distribution which makes every state equally likely, that's the maximum amount of disorder. Oh my God, don't do this action because after that you have no idea what happens. So don't do this action because you likely will get the most likely outcome, but there's also these other outcomes that can happen with some non-trivial probabilities. And when you have actions which have low entropy actions, you can try to solve the MDP as if it is a deterministic problem. In some sense, whenever we consider the world is made up of deterministic actions, it's not because it's truly deterministic, but because the likely outcome occurs with the most probability, and everything else is very unlikely. That's why you get by with deterministic calculations. Just like Einstein is right, Newton is wrong. Or Schrodinger is right, Newton is wrong. And yet we study Newton because the quantum effects and the relativistic effects don't occur in the classroom. Because they're very unlikely in that level. Yeah, go ahead.
Just to clarify, are you discussing entropy with respect to the results of an action?
Results of an action. So in fact, entropy is a property of the distribution. Entropy of a distribution. So an action with a high entropy means it will basically take you to all states with the same probability almost. Okay. Okay. So yeah. So anyway, so understanding an MDP agent involves learning both its transition and reward values. What is the answer to that? So you need to give the transition model, which is basically giving for each action this probability distribution of which states it will get into with what probabilities. And you need to give the reward, which is for each state it can find itself in, what is the immediate candy it gets, immediate reward it gets. Those are the two things. Then everything else just follows. Right? So my question is, if you are thinking that I'm an MDP, in fact, to a first order of approximation, these things are actually very useful to understand how people behave. If you're thinking I'm an MDP, you need to know what my capabilities are, what kinds of actions I'm able to do, and what my reward metrics are. What do I like doing? What states do I like to find myself in? If you know both of them, then you can predict where I will find myself in at any given point of time. If you want to model an agent, you need to know both their transition function, which is their capabilities, and their reward metric. What do they get their kicks from, quote unquote? And my philosophy is, to a second order approximation, most of us have somewhat the same capabilities. Most humans have more or less the same capabilities. So the thing that differentiates one human being from another is their reward metric. So this is not AI. This is just general. If you think AI, put AI cap, MDP cap, and try to understand humans. What you would really like to understand is what is the reward metric? Where do they get their kicks from? Because that will tell you what they are likely to be. Because capabilities are more or less the same. In general, you need to know both capabilities and rewards, but humans, all of us more or less have the same capabilities. Okay? Any questions? Any other questions? Okay, so then I'm going to continue and try to talk a little more about MDPs and computing the policies, at least in the finite horizon case. Okay, and then we'll come back and do computation of the policies in the infinite horizon case. Okay, so what is a policy? Policy is basically a solution concept. For MDPs, solution MDP is a policy. It's a mapping from states to actions. It tells the agent that if the agent finds itself in state S, it should do action A. And if it's a finite horizon, then it also needs to know how many steps do I have to live. If infinite horizon MDP, it'll just tell for if you are in this state, do this action. In a finite horizon MDP, if you're in this state and you have 10 more years to live, do this action. And it turns out finite horizon MDP is actually more complicated looking because the policy has a bigger size. Because you need to know what to do in each state for any number of steps left of the K steps, that the K horizon. Horizon is your expected lifetime. Okay, and so I need to know if you're going to live for 100 years and you're in state S1, what are you supposed to do? If you're going to live for 99 years and you're in state S1, what are you supposed to do? And you need to do this for every state. So you need a copy of the policy for every decrement of the horizon all the way to 0. That's the finite horizon policy. In the case of infinite horizon, it's just 1 because infinity minus any number is still infinity. Okay. So when the agent does the action A, it doesn't know for sure what exact state it will be in, since it's a stochastic action. However, the agent can observe the state S dash fully once it does the action, just like the toss up of the coin. After the action, during the execution time, the agent will know where it went. During the thinking time, it only has probabilities. This is like a very important thing you have to understand. For A star, thinking deterministic, world deterministic, world fully observable. For MDP, thinking basically it won't know after these many actions where I'm likely to during the thinking itself. Whereas during the execution, after every action, you know exactly where you are. Okay. One other thing, of course, is so deterministic search. So there is this distinction between planning time or the thinking time and the execution time, where you actually do the action in the world. In the deterministic A star search, at the planning time, you're searching for the optimal path from the initial state to the goal state. At the execution time, you execute the actions on the path, one after other. You can do this pretty much blindly because the actions are deterministic and you know where you're starting. Unless you suddenly believe that it used to be static world, but some crazy kid came and started doing random things while I'm doing execution. Okay. In the case of MDP, at planning time, you search for the optimal policy. Policy is just a generalization of the path. That's what I tried to explain to you earlier. Execution time, you just execute the policy. In government circles, in economic circles, they use plan and policy synonymously. You see what I'm saying? And plans and policies are like the most important things while you are running for election. Because everybody should have a plan for how to make US great. And they should have a policy as to how they will get everybody vaccinated. Plans and policies essentially are doing the same thing. The policy, the technical difference we have is that policy basically tells you what to do in each state. I mean, if it's deterministic, certain world, then vaccinating everybody will be starting them in online and vaccinate, vaccinate, vaccinate. But we know that's not the world we live in US. So then you will have all sorts of interesting things and they have to come up with what to do if this following thing happens, and that's the policy. Okay. Anyway, so that's MDP versus deterministic search. Remember this guy, and remember that the only things that change are instead of deterministic, we are stochastic. Instead of, we are still observable, fully observable. Instead of full goals, it is basically partial satisfaction of generalized goals. You will have the temptation to think that MDP generalizes everything. That's not true. MDP in particular is not dynamic. It is not dynamic. There is nobody else other than you. You're just playing a game against nature. And the nature doesn't care that you are there. So when you do this action, there is this probabilities that you will get into different states. Okay? And similarly, it's not partially observable. It is fully observable. Because when you get to that state, you'll know exactly what state you are in. And finally, it's not, it's not durative actions. It's just instantaneous actions. You do an action, you'll get to the next state. So the rest of the complexities don't exist. And for every extra complexity, there is an app or an MDP for it. So you want to throw in, let's say, durative actions into MDP, you will get something called semi-MDP, SMDP. You want to throw in partial observability into MDP, you will get something called POMDP. You want to throw in additional agents into MDP with all the agents doing their own actions, you will get something called DEC MDP, decentralized MDP. You can start throwing two things at a time, you can get DEC POMDP, or you can get DEC semi-POMDP. If you start doing anything more than MDP, life is too short for that, in general. You see what I'm saying? The real world is DEC semi-POMDP. Okay? Actually, it's not even that. The real world is DEC semi-POMDP with unknown action model or not fully known action model and not fully known reward metric. That's what real world is. That's what you're living. You're proof that this can be solved, not quite optimally. We can look at ourselves, we are not really optimal. But that's what real world is. But we are doing a little chunk at a time. So we are doing MDPs, which are at least doing the stochastic part. Okay. So it's important to understand. I mean, you can use this slide any which way. As far as I'm concerned, in this class, when you can say I'm using A star search, don't say this, which is equivalent. I'm using deep reinforcement learning and that POMDPs with one agent, full observability, deterministic actions with discrete and finite state space and positive transition costs and known transition and reward models. If you say this, you're saying I'm using A star search. So if you're writing a paper for new rips, say this. They'll be very impressed. For me, please say this. You understand what I'm saying? You don't ever complicate things more than is needed, because when you start deluding others, at some point of time, you'll delude yourself. That's a slippery slope. So you should understand what the difference is. It's a very nice thing. I gave you a huge number of things. You can write this actually on your resume. You know, when you apply for Google jobs, you can say, I do all this stuff.
Let's hope you're not hiring us.
What? I won't. No, that's a different story. I mean, a whole bunch of bozos who are in the hiring boards in every company who won't understand anything. So you can use that to your advantage. Okay. Okay. Yeah. Anyway, this is actually a very interesting case of telling you that in this scenario, I don't know if we discussed this in the lecture you have seen. Did I discuss in this lecture? Here is a case where it's like humans, the agent has the same exact actions. The reward function is changing and its behavior changes radically. It's a beautiful example. This is why it's important to understand. I always think that if I want to understand somebody, I want to understand their reward. What makes you tick? What gives you kicks? Because that will tell me a lot more, because we more or less have the same capabilities. Okay, by the way, this is why societies focus on incentives. That's incentives are also called mechanism design. People are more or less people. It's not like, there are like a vanishingly small fraction of people who know how to play basketball well. Vanishingly small portion of people who know how to do quantum mechanics. Most people are general bozos like us. They're quite impressive compared to your family dog. You don't realize that. But mostly they're all very similar in their capabilities. So if you want them to behave differently, what you do is change the incentives. Much of governing is changing incentives. Think about that. By the way, so everything has a fancy name. Changing incentives is what's called mechanism design. It is studied a lot in multi-agent systems. And similarly, looking at your behavior and figuring out what might be your reward function, learning your reward function just from your behavior, assuming I know the model. It actually has a very fancy name. It's called inverse reinforcement learning. That's just a fancy way of saying I'm trying to figure out where you get your kicks from. So I keep seeing that every day. In the middle of the day, you're going to the bar, you're not coming out until the end of the day. So that's your reward. So I figured that out. So I did inverse reinforcement learning on you. You see what I'm saying? And in fact, many things like, most of your social media try to model it. They try to understand your reward metric. Why does YouTube suddenly start showing some strange videos? Because it saw that yesterday you clicked on this other kind of video, which is somewhat strange. And according to its metric, these videos are similar to this. So you will show more of them. This looks good. You start clicking. And very soon, in fact, there is a whole entire sociological studies showing things like radicalization will occur just by this. Because all YouTube is trying to do is to increase the amount of time you spend watching the videos. They don't really care whether you're watching the videos involving killing people or you're watching the videos involving cute dogs. Some people may have seen one killing people video, it'll start showing more of them. If they're crazy people, they'll start seeing more of them, and they can start getting a lot more radicalized. So all of these techniques, basically, how many of you have seen the Netflix thing, Social Dilemma? Social Dilemma is IRL, Facebook doing IRL on you. There was a raised hand somewhere. Yeah.
This might be obvious, but why is there an arrow pointing off board for some of these scenarios?
What? Going what?
Like for the range 0.0221 and 0. Why is there an arrow pointing off the board?
Pointing where? I don't understand. This way, this one?
No, like the bottom right. No.
Up this one?
Bottom right. Same map for it.
This one?
Yeah, like how does
Yeah. That's a very good question.
that no state? Where does that?
Why do you think this is the case? You did not hear my lecture. I gave a very nice example. You know how I go down the Kaibal train in Grand Canyon? From outside perspective, it looks like I'm not going anywhere because I'll do this. Because what I'm trying to do is reduce the chance of dying. You see what I'm saying? It's an amazing thing. That's why that example is just so beautiful. So what this is doing here is if it does this way, there is a small chance that it can go into -1. Right? Because when you try to go left, you go left with 0.8 probability, right, which is up with 0.1 probability, or left, which is down with 0.1 probability. Going down is basically hitting the wall and staying here. Going up, you get here. You do this in real life. It's a great thing. I mean, it looks like an irrational policy. When people are doing irrational things in front of you, you don't say they're irrational. You say, what is their reward metric? What's making them do this? Right? I mean, you and I both are going down the, Kaibab trail. Maybe you are a better hiker. So you're just going directly, I mean, I still see these videos where people are just walking on like very worrisome scenarios, happily. Maybe some of you are like that. So either you have very good capabilities or you have a very different reward metric. Did any of you understand why wars are fought by young guys with older people like me saying, go to the war? How many wars do you think would have been fought if Churchill actually had to go and fight? 0. Younger people have slightly different reward metrics. In fact, this is actually true, by the way. The brain keeps continually maturing, quote unquote maturing. And the parts of the maturation part is the thrill seeking is higher when you're younger. When you get to about my stage, thrill seeking is maybe coming and talking to the class, not going off to Afghanistan and showing that I'm a patriot. You see what I'm saying? So people figured this out. And they send people. You remember that the selective service registration after 26, nobody wants you. Because they know that you send them to the thing, you're not probably going to actually take risks. You will think. In fact, there's a beautiful sketch by Seinfeld where he says, if a horse were to know, a racing horse were to know what would actually happen to it if it were to trip and sort of break its leg or something. But you know what happens, right? Racing horses, apparently, it's considered being kind to them, to kill them. I don't quite know why. I mean, if I break my leg, please don't kill me. I can do a whole lot of things. If, what's his name, Stephen Hawking basically could change the world with his mind, where he has no legs, no hands, and basically very few effectors. What exactly are you doing? Essentially. But for horses, we have decided, because we didn't ask horses. Horses have no say in it, and we just said, okay, they're dead. So Seinfeld says, if horses realize this, how would they race? Okay, maybe not a good idea to take any chances. The way I go on the Grand Canyon Trail. That would be a rational horse. Think of the connection between horses racing and young people going into wars. They connect to their reward matrix. Okay. So what I want to do before going off. Okay, so this is something that I want to show you. That reward versus cost-oriented MVPs, which I already mentioned earlier. So in one case, you think in terms of reward S, you can either do in terms of reward S, or you can actually say reward is connected to a transition, which is the most general case. If you go from S to S dash using A, then you get a reward, a specific reward. Whereas you go from S to S double dash using the same A, you get a different reward. That's the most general case. A star search basically says for each, if you take an action, you basically, the thing only depends on the action in the case of A star search, because each edge is an action. That's just a special case of the RSAS dash reward metric. On the other hand, you can think in terms of costs, which is CSAS dash. And then the goal is, in the case of policy finding, in this case, goal is to find a policy pi. You normally use pi for policy. Okay, that's just the convention. That maximizes the expected cumulative reward that you can get. So do the actions that maximize the expected cumulative reward. And the word expected has to come in because nothing deterministic about it. When you do an action, you can get this action will get you to state S1 or state S2 or state S3. S1 has this value, S2 has this value, S3 has this value. You can't be guaranteed that you will get one of those values. You'll only be guaranteed that you'll get the expected sum. Probability P1 times value 1 plus P2 times value 2 plus P3 times value 3. So enough of all this. So anyway, basically these are equivalent models. One thinks about cost, one thinks about rewards. They're equivalent models. Most of the time we will look at the reward model. Okay. So one example that I will give you today before we end the class is how to solve MDPs. Just solve MDPs. Even though I know that the MDPs are static, that means they're in the static world. There is no other agent. You can act as if this is a game against nature. And so you do the game tree, just like the min-max tree. In the min-max, you did mins, maxes, mins, maxes. Here you do at one level expectation, next level max. Expectation, max. Expectation, max. That's it. You're done. That's your online MDP solving algorithm. Okay, so for example, I start from this state 3-2. I believe 3-2 is like here. And then I can go up, I can go right, left, down. Right? So I said, if I were to go from here to right, from 3-2, I can go to 4-2. Because that's the thing, right? If I try to go like this, I'll go this way with 0.8 probability, this way with 0.1 probability, this way with 0.1. That's the example we're using. It's not any sacrosanct. Right? So you will get into this state with 0.8 probability, this state with 0.1 probability, this state with 0.1 probability. If you are smart, you can continue expanding this tree until every leaf node is a terminal node, if it is possible. Or just go deeper. But if you are not, if you are lazy and you want to feel like stopping here, then what you can do is you can take for every node at the bottom, you can act as if you have an evaluation function. The simplest, dumbest evaluation function for MDPs is the immediate reward. So take the immediate reward, assume that's the value of these states, then this guy's value would be 0.8 times minus 1 plus 0.1 times minus 0.04 plus 0.1 times minus 0.04. You see what I'm saying? So you will get a number here. Similarly, you'll get a number here, you'll get a number here, you'll get a number here. Now, this guy just needs to pick the action that seems to give the best expected value, the max. So you did game trees where there was an opponent who was actually trying to do the maximum damage to you, because of which, instead of expectation, you had to assume that they will take the version that would be the worst for you. Okay, whereas here you're assuming it's just nature, so it's like basically expected value. This is online decision making for MDPs. Everything else you learned about min-max search can be done here too. For example, you can go deeper. If you go deeper and apply the reward at the lower levels and back it up, you will get a more informed action choice. Just the same way you got a more informed game choice in the case of chess. You see what I'm saying? So in fact, there's a way of doing that. Basically, it's called, this idea is called real-time dynamic programming. A fancier name instead of min-max search. In the real-time dynamic programming, basically it does, instead of max and min, it does max expectation. So expectation maximization, expectation maximization, expectation maximization. Expectation of all the actions that you that for each action there is a stochastic outcome. So there's an expected payoff from this action that is computed in terms of its value, current value. Since you don't know the value, just like in the game trees, it's computed in terms of its true board value. Since you don't know the true board values except for the boards that are terminal boards, you do evaluation functions. In the case of MDP, you can also do evaluation functions. But if nobody says anything, you just take reward, immediate reward as the evaluation function. But if you go deeper and apply the reward function, you get a better estimate. If you don't feel like doing RTDP this way, which is basically anytime you want to go deeper, you have to kind of expand the entire tree. Is there something else you can do? Monte Carlo tree search. The only difference is the propagation will be different this time. Remember in the Monte Carlo, we did propagation based on mins and maxi. Here it will do it in terms of expectations. So at the end of today's class, you at least figured out there, if your life ends today, I hope it doesn't, you at least know how to do online decision making for MDPs. This is actually good enough. Most MDP solvers for large scale MDPs do something like this. Either they do RTDP or they do Monte Carlo tree search. But because we are computer science people, we want to first ask, I'm getting some values here. You're saying all this namby-pamby thing, like it can be better if you go deeper, etc. But if I actually have the entire, what is the true optimum? Assuming computation is not a problem. If I have infinite computation time, what is the true optimum? How do I compute it? That's what we will do in the next class. We will actually compute, finite horizon optimal value function. And then I just want to show you that when we were talking about it, the finite horizon optimal value function will have pictures like this, essentially backing up expectations and maximization. Except if you're trying to figure out what is happening, you can turn this thing around this way. That's just expectation maximization. Except this discussion will tell you the true optimum finite value function and also optimum finite horizon policy. And what did I say? Computer scientists want to know what it is and then forget it. If you're a hacker, you will forget your next class, just as you forgot, I guess, this class too. But but if you're a computer scientist, you want to know next class because you want to know what is the optimum. What am I missing by not computing? That's finite horizon value converting into policy, infinite horizon value converting to policy, and those are all optimal algorithms. And having said that, we'll realize they're actually very costly in real life. And so you go back to something like that real-time dynamic or Monte Carlo search much more. Stop here.
Wait, did you did this like,
I don't remember.
yeah.